electric field anymore. At fourth floor, it's likely that we are going to move to A floor for temperature and electric field to start to look for neurons. Indeed, we are making a major modifications for temperature. All the temperature plates, including a linear one upstairs, move to A floor, and we are going to have 4 plates, and only one is for wow tracking. The rest is for Canon 60D camera. That is the main change. In a couple of days, we have everything ready. By Friday, I'm sure it's completely changed. Electric field has some problem of power supply. It may be fixed this afternoon, maybe not. For that reason, A floor is primarily for temperature data taking. If in any case, both are hardware upgrade. I think not. I can just let you know. And finally, B floor 3D system. Joe is back, and I think Rachel and Harrison are working together to activate 3D first with the phototaxis. In 2D phototaxis, it's still with modification with the line confocal to watch neurons, so it's not quite ready. But in any case, looks like we have enough manpower for B and 3 and T plus E as a whole. This group has a lot of senior member, but we may want to have more new member in a week downstairs to take 3D data and phototaxis data, just to let you know. That's more or less it. And we have a lot of software guy working, but eventually you should be a part of data taking, not only this floor, but also A floor and B floor. Questions? So that's the main activity. And as I said today, Richa is going to update biosample preparation and give a lecture on microscope. All right, so I'm going to open this slide. That is this slide. So
could you go back to the first one?
This one?
The first slide?
Yes, first slide.
Yeah.
Yeah, this one. And I can go to
Hey guys, so I'm Richa, nice to meet you. You may have heard my first presentation a little bit earlier this summer.
Come close.
But if not, I guess if you did, this is gonna have a little bit of repeat.
Seat. Move
so,
here.
It's okay, I'm short. You can probably see from the side. I don't block the screen. Okay. Yeah, so if this is new for you, great. If not, sorry for the repetitive information.
It doesn't work.
No, I think I just swing it backwards. Yeah, so here I have a diagram, a schematic of the life cycle of a C. elegans taken straight off of Wormbook. And so as you can see, there's like, from the egg, there's about a 14-hour development period, at which point it hatches, and then there's 4 main stages of development after that, L1 through L4. And then young adults, at which point they become gravid, which means they're like pregnant in a sense with eggs. And
Question, I
elegans,
just
yes.
realized there's no clear cutoff between L4 larva and young adult?
It
Do they
is.
sleep?
No.
No.
No, L4 and young adult is the same. It's just there's a point where they start developing the eggs.
L4
So a
larva.
point of like self-fertilization and egg development. And once eggs are developed, that's when it's an adult. So between this and that is like young adult, I guess.
Continuous.
So it's still an L4, but it hasn't completely gotten its eggs yet. So we normally like to test them at this level, L4, which they're adults. They're fully developed. We don't like to test them up here necessarily because when they become gravid with eggs, they lay them pretty quickly, and once they've laid eggs, they die. So
someone wanted to shoot a blue light for the pregnant one. Who was that? There was an idea of stimulating.
You could. You could, like, it's just, they're like
That guy
old
here.
and dying. He's
Dying?
somewhere. I don't know. Like, you could work with like, gravid adults, but you just have to be careful because if they, like, once they lay eggs, they, like, kind of just sit there and don't do anything and die soon after that. So they fulfill their life cycle.
Die?
But yeah.
How many hours later?
I mean, I don't know exactly, but, like, for example, one time we were taking electrotaxis data, and we looked at the video, and the egg, like the worm laid the egg, like right there, and then it just stopped moving. So.
How was the data analyzed?
Oh.
Yeah, I saw that.
Oh yeah, yeah. So like, It's not
Slave
ideal,
Okay.
but it can be done. But yeah, so what I was saying is earlier is that worms, they're hermaphrodites, or some of them are hermaphrodites. Most of them are like female, I guess, like in the technical biological sense. And so like they're either hermaphrodites or male, which means most of them are capable of self-fertilization. So the worms we have are all clones of each other because they've all been self-fertilized, which is nice for us because then we know they're genetically all identical, especially when we're working with strains where the genetics is important. Like this next slide, we have like all these working strains right now. For example, like ASJ-CAM is a flashing ASJ neuron, and we need to make sure all our worms have flashing ASJs, because if they don't, then like it's kind of useless to study them, because that's particularly what we want to study. So it's nice that they're all genetically identical to each other, because that way we have a guarantee that they're going to do the thing that we're looking for. So as you can see, we have a lot of current working strains. You guys probably, especially like the new members, if you're working, you probably work with M2s, which is a wild type strain. There's nothing really all that special about it. And then we have ST2s, which I guess it kind of looks like this is a computer modeling of the C. elegans and like all the neural networks. And so ST2, like all the neurons are fluorescent. QW1217 is quite similar, except the neurons are flashing, and that like every time they're activated, they fluoresce. So that's the difference between, I guess, like just fluorescing and flashing whenever I say those. So yeah, the ASJ-CAM, like I said, has a flashing ASJ. AX2047 is AFD, and then we have Light 1 and TAX4, which are
For
new,
ASJ,
and I
right?
don't know exactly.
Both are ASJ marked,
Oh, really?
but mutant, on top of mutant.
I see.
So,
Okay.
so we have 3 different types of ASJ.
We have-
Especially light one is very important because ASJ neuron is sensitive to the blue light. So if you want to study ASJ for temperature or electric field, you may want to use the light one ASJ, not original ASJ.
Not the ASJ-CAM. Okay, I'll keep doing that. Yeah, we're still running those, but they're making good progress. And then EH294 we've had for a while. That's a fluorescing AIY neuron. So the AIY neuron is just constantly bright. So yeah, different strains for different uses depending on the experiment. What I do down in the bioream, part of it is just basic maintenance of our worm strains. By that I mean, you can imagine, so we grow our worms on a plate full of this OP50, which is the strain of E. coli that we use to feed our worms. And there's only a limited amount of OP50 on each like petri dish. So every so many days, I or Fat Rata pick some up from one plate and transfer it to another, which allows them to like, it's a new food source for them, and then we like pick up adults, like L4 adults, the gravid ones, so that they lay their eggs on the new plate, and then you get a new generation of worms. We also work with M9 buffer a lot, which is like a solution made with different salts, and that's something that C. elegans can survive in. So we use that for a lot of things. You guys have probably used it for making gelatin at some point. We use it to wash the worms of OP50. If like in your sample you need worms that have been totally starved, no food source for a certain amount of time, we would wash them with M9. I also do this thing called synchronization. We haven't really been working with that this summer, but basically what it is the idea is you want to make sure that all the worms on the plate are the same and the same stage of development. And you do that by essentially picking up a lot of worms, like gravid worms, then using a highly alkaline solution to melt off the adult bodies. And the adults will like disintegrate, which is gross and scary. But the eggs have a protective chemical, I guess, in the shell, which keeps them from disintegrating from the basic solution. So they survive. And then we just like have them suspended in M9 until they hatch. And then so that way when we take them out, they're all at the L1 stage, which is the just hatch stage. And then from there you can just time it, because as you can see from this slide here, we have a pretty good sense of how long it takes for them to develop from one life stage to the other. So that's fun. If you want to work with L1 worms to like compare to L4 worms, especially if you're like tracking how neurons develop throughout different life stages, this is what you would do. You would synchronize to get L1 worms and then compare that behavioral data with data taken from L4 worms. So yeah, samples, materials, and that was supposed to say methods and materials, but I made a typo, and it's a lot of words. So moving on to the different samples. How exciting! this is a typical Phototaxis 2D sample. I don't know, do you want me to go into detail about like each sample?
Maybe not much detail.
Maybe not much detail. Basically, like what I have outlined in all these slides, I don't know why it did that, that's weird. Basically, what I was trying to show is that every sample is made with a certain number of materials, and those materials are carefully chosen depending on what we're trying to observe. For example, in a 2D Phototaxis sample, we're trying to observe how worms react to blue light. And so we want to make sure that the medium that the worm is floating in is something clear, because if we don't have that, then we're not sure what wavelength of light is reaching the worm. And so that's why we use gelatin. Gelatin has about the same, 2% gelatin has the same index of refraction as water. So that's pretty clear stuff. For magnetotaxis, we use, of course, cuvette, because we need something clear for us to see the inside of the cube, I guess, to see the worms like swimming around there. You can't see it on here, but they're tiny. This is a new sample, I guess, free motion. I mean, it's not entirely new as an experiment, but it's something that we haven't done in a while. So we started it up again this summer, especially for the new members.
Who are working on free motion?
It was
Are you
these
working?
guys.
2 of you?
Hey guys. So yeah, this is what U-Earth is. So it's probably super familiar. And it's
Are you ready for 22 centimeter? I haven't seen the data analysis out from 10 centimeter yet.
Oh yeah, I mean like one of the guys who is analyzing the data is not here.
Who's Brazilian guy?
Yeah.
John.
Yeah, he's not here. So he had the data on his computer, I think.
exciting
Why
stuff.
don't you analyze yourself? If someone can help, right? We don't want to wait because one gets sick. It's relatively easy.
Okay.
It's the same as any other analysis.
Alright, yeah, yeah.
Could someone help? Just the 2D data.
Well, I can
Oh, yeah, we can do it ourselves, yeah.
Why don't you do it yourself?
For now, we're
As
just
soon as it
using-
works, I want to go to 22 centimeter. It's more challenging.
Okay.
So we don't have any 22 centimeter plates, but we do have 20 centimeter plates. I
Oh,
can
is
put
it
that-
20?
Yeah, it's
I
20.
thought I bought the same.
It's
Anyway,
22.
we have.
I mean, I'll double check, but I thought it was 20. I'll double check.
Okay, okay.
Anyway.
Yeah, 20 is fine. Yeah.
Anyway, yeah, so right now what we're using is a 10 by 10, which is, I guess, relatively small. But yeah, we have like a just 2% agar pad on it and put some worms on there. And we starve them. So we starve them for an hour, which is, again, like another use for M9, for example. Just keep them floating around in M9. It's probably very uncomfortable for them, but we haven't proved their conscious yet, so it's fine. This is a thermotaxis sample. It's really hard to make. It's just like a really thin layer of agar, I guess. And we use like a thin layer of agar because agar doesn't melt as quickly as gelatin. So another example of like how we choose the materials for the sample to match the thing we're trying to observe. So if you can imagine if we had like gelatin there, it would all melt and then they'd be swimming around in what's basically water, which would not be very helpful for us. This is 2D, the old, I guess, 2D electrotaxis setup.
We used to have a 1.7% so sounds about.
We've been using 1.7.
We've been using
it's what the
1.7
paper,
always.
both the papers
A
using.
lot of salt. It's like more than seawater. Seawater is 1%.
It's 1%.
They've been using that, so we use it.
It's 1%.
What?
Oh wait, agar.
Yeah.
1%. 1%.
Well, it's like 1% agar, but
Agar.
it has salt in it.
It's like 1 milliliter.
Oh yeah, no, it's
Okay,
no.
that's
like
mistake.
salty
It's
agar.
so salty
Yeah,
for
yeah,
me.
yeah.
Yeah, misunderstanding.
So
Okay.
It's no reason.
I'm sorry for the typos, I apologize. But yes, it's salty agar, 1.7%. Slightly more liquidy than the normal agar we use.
Yeah.
But the reason we use 1.7% instead of something higher also is like also ease of transfer of ions. So, but I think we're probably going to change this soon.
Yeah,
we're
I'm
like
suggesting
working,
to
we're
reduce
like
as low as
developing
possible.
a new 2D electrotaxis sample, but honestly, we haven't figured it out yet, so I don't have it. And this is the 3D electrotaxis. How exciting! Sorry, this is like again confusing. It's a 1.7% agar or
Minimum.
gelatin, but with salt.
gelatin with the salt.
Yes,
Salt is tiny, right?
salt. Not
I'm
much.
just using 2%.
We've been using 2%
2% gelatin.
Okay.
Yeah.
With a tiny
Just for the easy
salt.
Yeah. Another reason with gelatin, it's a little tricky. Oh, this is what it looks like in real life, I guess. It's kind of gross, but there's like
It's just kind of.
copper tape.
Did you measure
That
resistance?
was an earlier one. We fixed all the problems. One of the problems is if you don't put the tape on it smoothly enough, there's air bubbles and they heat up, and then they push the tape off, so you can see there's a lot of bubbling on it.
Why don't you measure
Earlier one.
tomorrow? at the
I think I'm
party.
going on Thursday. But
Thursday, I forgot. It's a Thursday.
I don't know what day.
Electric field. is
Electric.
tomorrow.
Oh,
Electric
she's
is-
gonna do it
3D
Thursday.
electronics is
Ah,
Thursday.
as a
This
part
is
of
like
3D.
group.
3D.
You,
Yeah.
as a part of 3D also. Fine.
He is 3D.
Honestly, this is new to me, and I have not been super involved in this part. It's mostly been Andrew and Rachel and these guys.
So of course the idea is you have electric field. So this direction,
Just
the ceiling has moved along the
Like-
cone shape. And
In a
that's
cone shape, but
quite
theoretically along the same angle as they would,
right.
like
That-
as
that's
observed
what we
in
tried to observe.
So that's exciting. Still trying to figure out the kinks. Like, for example, like I said earlier, gelatin melts a lot faster than agar, and so sometimes when you run a current through, it just gets like
we
weird
haven't
and
had too much
bubbly.
melting problem. It's more the browning issue. We sort
Yeah.
of figured out the browning stuff.
It's like
Now we're trying to
Yeah,
get
the
current
browning
going a bit better.
when we like ran for like 2 minutes before, it's just like weird.
Yeah, but it's been looking good. It's looking better at least.
So that's fun, developing new samples. And that's all I have.
Thank you.
I think, yep, that's it.
Okay, thank you. So actually, thanks to Richard and Ada and Fatso for our sample, it's great. And as you know, we set a kind of policy that they come at 10 o'clock in the morning, they prepare advanced sample for all of you, except maybe B group or other relatively easy setup here. And if you need a sample, different type of samples, 3D or 2D phototaxis downstairs, or you need HD2 or QW1217, you have to tell Richard 24 hours in advance.
I usually say that for like any 3D sample, it's more important to know 24 hours in advance.
2D samples,
3D,
3D samples,
Yes.
3D sample takes time,
because they take like about.
including a magnetic field guide.
They have to set, especially magnetic field, but magnetic field knows what they're doing.
Okay.
They're good, yeah.
So 24 hours notice,
Yeah.
always. Think ahead, a day in advance, what data you want to take next day. Right? Otherwise, I think the quality is good, so you don't have to worry too much. Now I'm going to talk about microscope, and this is a lecture I gave to a 180G physics major about a couple months ago, and it may not fit today. Today I will split half. So I have a basic introduction of how optical microscope works, and then main part is today's advanced microscope in two directions. One is so-called super resolution to break the diffraction limit, like going down to 100 nanometer resolution, like a micron resolution, which you typically have. The second one is how to make a high-speed data up to 3 dimensions. That's what we're doing. And by combining these two, idea is of course to watch all neurons, not just the C. elegans, but also zebrafish and mouse, 10,000 neurons within a second, and look at the dynamic signal at the end. And we wrote some proposal to National Science Foundations, hopefully approved in a few weeks. So that's the kind of idea. I may stop somewhere here today and split into tomorrow. May have more time actually. Wednesday is crowded by software guys. So let me just start from concept of optical microscope. Of course, you like to see some object, and your brain is opaque, you can't see inside. So you have to find some way to penetrate deep enough. And there's a few windows. In case of tissue, actually, tissue is transparent enough around 1 micron regions. There's absorption band, so-called absorption by water somewhere here. But roughly speaking, of course, the reason why we use optical wavelengths here is, of course, sunshine has a maximum energy between 400 nanometer and 700 nanometer. And also, the reason why it has most of the energy is air is transparent for that. So we try to utilize this because this is easy to observe. Now, the history of the microscope is relatively recent. The original idea of microscope was developed quite a long time ago, like 1565. But the first real microscope, especially for fluorescence, comes only 100 years ago, and nothing happened so much. But then there is some advantage taken by interference, called differential interference microscope. I'll tell you in a minute. And then only 50 years ago, so-called confocal microscope using fluorescence that started to happen. And then the 20 years, the two photon excited microscope, and finally for the last 10 years, all kinds of so-called super resolutions. And people had, okay, I tell you what diffraction means. Now, let's just take a very simple way to observe some tiny object. Basically, you take a signal out, and then you have an objective lens, and then after the objective lens, it becomes parallel, and then you focus back the point. Now, you may think the most important is magnification of your microscope, because the microscope is a device to magnify. Not anymore, because the pixel size of a camera is tiny. In this, if you take a cell phone like this cell phone has a million pixels. Each pixel is actually 1.2 micron square today. Right? Now, the scientific camera like that one, or not this one, maybe this one is small. Typical science camera we have is about 5 micron squared. So pixel size is not much different from the wavelengths anymore. The purpose of the microscope is to collect the light with a large angle, so that it comes from the one point and collect more efficiently. And it is given by so-called numeric aperture, NA. And if the opening angle is alpha, sine alpha times index refraction of this material here, it's called numeric aperture. This single number is the most important number for microscope. And roughly speaking, good microscope has numeric aperture of around 1.0. The reason is the resolution comes from interference of the light, so-called array disk, because of this basically the quantum mechanical phenomenon superposition of the light. You see this kind of pattern called array disk. And if you slightly move your point from the red part to green part, basically the resolution is defined at the point where this overlap is half the height. And it is given by wavelengths divided by 2 times numeric aperture. And this is the most important equation for any microscope. So typical good objective has numeric aperture of 1.0, and the lambda, for example, the red is 700 nanometer, green is 500 nanometer. So let's take a 600 nanometer divided by 2 for n equal 1. Typical microscope has a resolution of 300 nanometer. Now, how to compare with a biological sample? You have to have some common sense of the size. Typical cell size is 10 micron. Big one is 50 micron. So if you have a 10 micron object, you are slicing pixel to pixel at 300 nanometer means like every 100 per 100. If the cell is 300, if the cell is 30 micron, if you are sampling every 0.3 micron, and then you are basically making 100 per 100 pixels out from cell. So microscope is primarily designed for cell biology to look at structure of the cell. On the other hand, if you want to look at the genetic structure, DNA itself, DNA, the only number I remember is the double helix is 2 nanometer. So now you cannot see the structure of DNA, but you can see where the nucleus is, more or less. You can see more or less where the protein is located globally, that's it. That's the limitation of optical microscope. Whereas if you start X-ray, typical wavelength of X-ray is a nanometer range. So if you shoot a nanometer X-ray, you can see the structure of DNA. That's the discovery of double helix. Okay? So you get an idea? So all this number becomes important when you design the microscope. Commercial microscope, as you know, look like this. Typically, and inside it looks like this. So one thing you need to know is there is a detection objective and also so-called condenser lens underneath, typically. And scattering light, if you want to see just a scattering light of C. elegans or whatever object, basically the light comes from the bottom and shoot a light here, and then you look at the scattering light from here. There are 2 ways to look. One is to by looking by eye, the other is look by camera. Now, let me just mention magnification. Magnification means basically if you happen to have so-called turbulence when you focus to your sensor with a focal length of 200 millimeter, then you achieve that magnification. So typical microscope downstairs has magnification of 10x or 20x or 40x. Let's take a 10x as an example so that you can quickly calculate. If you have a 10x and 200 millimeter tube length, what happens is you magnify by factor 10. And your typical sensor detector has a 5 micron square pixel size. So each pixel corresponds to 0.5 micron. And that is a good match with the diffraction limit. In other words, there's no reason to go beyond magnification of 10x or 20x. If you have a 20x, 200 millimeter, 5 micron pixel, it corresponds to 5 micron divided by 20, which is 250 nanometer, correct? Now you get the sense why we have such a low magnification in our laboratory. You may think you want to have magnification of 1,000. No, useless. You only want to magnify factor 20 or 40 in any system in our laboratory, and then you hit diffraction limit already. What's more important is to have a large numerical aperture, and typically if magnification is larger, like 40x, you can easily get 1.0. The third important parameter is working distance. If you want to have enough space, your objective is far away, so numerical aperture gets smaller. So here is, to the end, a commercial objective, and good objective like this one is numerical aperture of 1.4. And that is one of the high-end objective with 60x, working distance, by the way, the short, 0.2 millimeter. If you go downstairs, most of the microscope we have is 10x or 20x or 40x, and numerical aperture for 10x is 0.28.
Yeah.
20x for 1.45.
It's just 0.4, yeah.
Something like that. So we sacrifice using long working distance. Most of the case, we want this to be far away, so we have 2 centimeters, 3 centimeters, not just a 0.2 millimeter. You get 3 numbers, more or less? Okay. Now, if you want to look at scattering in light, there's a basic principle, and that is called Taylor illuminations. Taylor illumination is a standard illumination technique, and you have to understand the basic principle. Basically, if you have a sample, and if you want to see this point, after the objective, basically you focus the point. This is the standard geometry. Right? So, in the standard geometry, the light comes from the point. But when you shoot a light, you don't want to have, so if you start from the light and focus the point, you see a structure with a lamp. That is a disaster. We take approach called conjugate. Conjugate means instead of the point, you want to have a parallel light here. So what happens if you have a parallel light at the sample side? Basically, after the objective, you make a point. So this is called back focal plane. So any objective, if you shoot a parallel light in the infinite, sorry, this is not a parallel, but typically microscope is designed in an infinite space, meaning you have a parallel light, you come to the point. On the other hand, if you have parallel light, it comes to the point. This is the focal plane of standard geometry to observe an image on your sensor, and this is called back focal plane. So Taylor illumination is a way to make an image or a light at the back focal plane, so that after your condenser lens objective becomes parallel, and then it's completely uniform on the sample. Okay? This is how you design the microscope. And indeed, we take some concepts like this for blue light simulation. When we do a blue light simulation, we want to have a straight beam, especially in the 3D. What we design is to have a point, and then make it parallel afterwards. And this size of the parallel beam depends on divergence of the beam. So they carefully designed to have a relatively small divergence and focus the point and make a parallel beam of order half millimeter. So once you understand this very simple concept, of course, how to align every different component is tricky, but that's all we do. Right? So then there's a different type of illumination. Actually, most of the case, if you want to see a Sirenians, we have a red light, and you, from experience, you know you want to shine the light from the sideway. It's called dark field. the dark field is to shine the light from the side, and if nothing happens, if there's no sample, it escapes away. So it's completely dark if there's no ceiling. Only if you have some sample here on the surface of the sample, the light scatters into your objective. So your sample is white, red color, on top of the black background. That's most of the experiment we are setting up, like electric field temperature plate. And also 3D system is based on this. Okay? Only exception in our laboratory is probably free motion, for example. Free motion is more like this Kela illumination. It's not a Kela illumination, but you actually make a flat light pattern, right? It's similar concept. Now, DIC actually is called phase contrast because what happens is you are going to have this prism to rotate, well, basically change phase depending on where the signal comes from. What happens is if your objective looks like a same gray but has a different index refractions, depending on locations, you have constructive interference or destructive interference. So you can see more sharp contrast if the sample has a different diffraction index of diffractions. It enhances the contrast depending on the boundary of the sample. Like it's similar in a way like ultrasound imaging, which enhances the boundary. But we don't have a DIC. But the DIC is a standard in high-end microscope. Now there's another technique called TIRF, total internal reflection microscope. We are talking about all illumination. This illumination comes at extremely shallow angle. If we shine the shallow angle on the boundary of two different media with different index refractions, actually this reflects back by total internal reflections. If you have water and air, of course with some angle, it's completely total internal reflected. The point is there is a slight, like a half wavelength of penetration of waveform, and that actually slides at the bottom like 100 nanometer. Right? Less than half wavelength, it's penetrated by quantum mechanical effect. So basically you can slice only the bottom part so efficiently that if you take an image, automatically it is a sliced image which is on top of this cover slip. And indeed in a CNSI, with the dissection microscope room, you have a TIRF microscope, which is my contribution actually. We should use it. We have a TIRF. The reason is we have a fastest camera. So we constructed TIRF microscope, but nobody is using that. So you're welcome to use it if you have a good idea. Now, move on. The revolution actually came from fluorescence microscope. So let me just start from science first, physics first. Fluorescence microscope is basically you have some molecule and you shoot a blue light. This is violet light. And then what happens is this violet light excites electron trajectory or some structure of fluorophore. Basically, you excite it from S0 ground state to S2 excited state. And what happens is shortly after that, within a 10 to the minus 12 seconds, very fast, it comes down to S1. And then it stays on S1 for a few nanoseconds. And emit a light and go down to the ground state. So it's two steps. This is a large energy, so blue light. So blue light goes down to a slightly lower state and then gradually go back to ground state. So energy from S1 to S0 is lower than blue light, so it emits green light, typically in a few nanoseconds. So that is the principle of fluorescence. So fluorescence emission is isotropic, and you probably know about green fluorescence protein, which was extracted from jellyfish by Shimomura and attached to C. elegans by Calfi. This guy, actually, I met him a year ago when he was visiting here. Roger Chang is basically a biochemist to utilize that. So these three people got the Nobel Prize in 2013, maybe. Why it's important? Because, as you may know, that this fluorescence protein can be genetically coded. So this is unbelievable. Basically, they figured out how to take a small piece of DNA out from jellyfish, put into any sample, like a part of DNA of this guy actually put a part of this DNA into C. elegans DNA and successfully expressed and got a Nobel Prize. Right? So C. elegans helped in the development of GFP. So when we say ST2 sample, every neuron has GFP. And flashing, not only neuron, also dendrite, axon, everything is flashed. So it's an extremely detailed structure, like this structure. That's what we have, thanks to these guys. But they don't flash GFP itself. It's a static image of showing a protein distribution for nerve fiber and membrane. Okay. Now next, the other big advantage of microscope came from confocal microscope. In confocal microscope, you start from the laser. Why we use the laser? This is also important. I'm talking about the science here. Laser is a coherent light. So when the laser emits a light, by definition, every photon is a coherent state. It completely parallel. So if you start from completely parallel, you can focus to infinitely small dots point to the diffraction limit, and then focus back to the dot. If you start from the lamp, tungsten lamp, like that, you can't focus the point. So this laser made a big difference in microscope. Make sure you can focus the point. And what happens in confocal microscope is you first focus the point. When the signal comes up, you have so-called dichroic mirror. Dichroic mirror reflects a short wavelength, but transparent for longer wavelengths. So blue comes here and green goes here. When it comes back to the photodetector, if you have a tiny hole, which is basically a focal plane of this point, it's called confocal pinhole. Basically, you can eject every scattering light not coming from this point or scattered back from somewhere else, like that. So that's how we can improve a resolution so much. This is the point confocal microscope. Now we speak a lot about line confocal microscope. Line confocal is a kind of cheap version or a faster version. Instead of the point, we are making an image of the line here, this direction. Starting from a laser, if you have a cylindrical lens, you can make a line. And this line is mapped onto the line or slit here. And instead of slit here, what we are designing downstairs is electric shutter, meaning this camera can read out line by line. So if you can activate only single line, here it is equivalent to have a line of slit. So now we can take a confocal from line to line. Clearly this is not as good as point, but much better than not having any confocality. And that's fast. And that is the origin why we can scan three-dimensional volume so fast. If it's a point, you have to scan point in 3 dimensions. And typical scanning per point is like 100 megahertz at most. Typically it's 10 megahertz. Okay? So what we can do is instead of moving 1 point, we can move a 9. So at the same time of scanning 2 dimensions, flat plane, we can scan 3 dimensions. Get an idea why we say line confocal is to take advantage of confocality of point confocal, but scan 3 dimensions, not 2 dimensions. That's what we are doing. Okay, now I go to super resolutions. Now, Sundermeet became quite popular for the last 10 years. It's kind of remarkable. These guys started to talk about that in early 2000 and got a Nobel Prize within 10 years. It's unusual because I don't think actually there's no major scientific discovery coming out yet from super resolution, but it became so popular. Like Obama is getting a Nobel Prize or Nobel Peace.
Oh yeah.
It's similar for me. They got a Nobel Prize by hoping this is going to revolutionize science eventually. That's my view. Of course, it's a great technology, and I know Eric. He's a smart guy. Stefan Hell also can. So actually, we are close to Eric and Stefan Hell. through Simon Wise collaborator on campus. They are smart indeed. They are physicists. I tell you how to break diffraction limit. Now it comes again from physics questions. The problem is that distribution of wave functions of diffraction limit is like a Gaussian distribution, and width is like a wavelength. So in order to break that, if you have, let's assume you have point confocal and you make a point here. Typically this point is like a plus or minus 100 nanometer. What you do is on top of this, while it is at excited state, you shoot a red color state beam with a donut shape. What happens is while you have this global distribution of excited state of Gaussian distribution, you deplete the edge or this part, and you only keep a central part alive. It's called stimulated emission depletions, and only central part, like a width of 66 nanometers, survive. So this was the first realization of super resolutions. And CNSI had the first commercial project because Stefan Hell, who is the inventor, was a close friend of Simon White, who is a collaborator, and that was a starting point of Nanocenter. So 5 years ago, actually, we got funded to get a $1.2 million, the first state microscope. So this is the kind of improvement of the resolution with that state in one dimension. This is the beam profile. With state, it improved like this. Basically, state microscope achieved order 50 nanometer. But this is slow because by nature it is a point confocal. You can't speed up. And you need a lot of photons. It's damaging a sample, so it's not so practical to the end. That's my conclusion. It looks nice, but you need a lot of photons. You have to scan slowly. By the time you scan and get to 50 nanometers, your sample is dead. So there is much faster way which we try to incorporate in the system. It's a kind of smart idea. Idea is to use structure illumination. Structure illumination is basically, think about a pattern illumination like this pattern. So you take an image using this pattern, and next image you shift by half wavelengths. Actually, by taking an image by shifting half wavelengths, you have two different informations. Each image carries a different phase. So by mathematical offline calculation, you can at most improve resolution by factor 2 to go down to 200 nanometer resolutions. And you can do even better by so-called saturated excitation, meaning, again, nonlinear effect. You can basically have a pattern like this, and then it has more information than half of the wavelengths. But typically, you get a resolution of 200 nanometer. But it is fast because it operates for the entire frame. So with basically, realistically, you scan this by, say, 20% of phase, take a 5 image, and then you get a factor 2 better resolutions. And this is relatively easy to improve. Our proposal, by the way, is taking advantage of this in 3 dimensions. We have some idea to make a 3-dimensional illumination. The other kind of brute force idea is to activate and look at this, but then look at the center of the mass distributions, kind of. And then basically, as you know, if you have number of n photons, you can get a center of the distribution at root square n times better resolutions. It's called photoactivation localizations. You can take advantage of this kind of, there are many different techniques, but basically you take advantage of distribution of photon and try to get a center statistically. And you can go down to, again, 50 nanometer resolutions. So that's getting quite a standard way to incorporate. There's nothing secret. There's no message here is diffraction limit called average limit of half wavelengths. It's gone. With a smart technique, there's many ways to go down to 100 nanometer resolutions. All right, now go to fluorescence lifetime image. Okay. So what is flame? Maybe you haven't heard about that. The flame is another great technique. And roughly speaking, if you know chemistry, typical size of protein is like a nanometer to 10 nanometer. It's much shorter. The distance between here and here in protein is only few nanometer, mostly. How can we measure? Of course, what's important is the three-dimensional structure of the protein and changing in time. In order to measure that, what you do is there is an overlap of, let's assume you attach fluorescence dye for green and red. And there's an overlap of wavelengths. And depending on distance, decay time for the red to green depends on the distance. So what happens is, roughly speaking, the difference of nanometer in three-dimensional structure of the protein can be measured by a decay time of fluorescence. In other words, it comes from overlap of the wavelengths. Nanometer difference is going to change the decay time of nanosecond. So if you can see a decay time of fluorescence, and if it changes from here to here, we can say that three-dimensional structure is changed in nanometer order. It's called free. Why I like this? Because I was designing the fastest photon detector to do this maybe 5 years ago. So here's an example that basically by looking at the film image, you can see more detail of the different shape of the protein like that. Okay. Now, what I am basically I'm the world expert is a high-speed photo detector. So besides doing some neuroscience, on the other side, I am designing the fastest microscope for user community and also work with the company. And the reason is, of course, the life is a 4-dimension. So measurement with high super resolution in space is only a part of the story. Your brain is running like 100 Hz. So unless you can see millions of neurons at 100 volume per second, you are not looking at the real activity in the brain. So now it comes to the speed. How can you sample a 3-dimensional structure in high speed? Now, the bottom line is easy. It's like a computer. Basically, it's a clock speed. Now, you take an image. So let's take, you have CCD or CMOS camera, like that camera. And this camera is typically running at 30 frames per second. What it means is it has a number of pixels. Number of pixels times that frequency is basically data transfer rate. And this data transfer rate basically is determining the sample rate in 4 dimensions. In confocal microscope, you have to scan point. So it's limited by a digitization speed of single point. All right, so this may be too much detail. Let's think about how to speed up wide field. So about 10 years ago, I just realized, of course, to speed up, we want to have basically high-speed camera. So now it's everywhere, but 10 years ago it wasn't so popular. So I was probably the first guy using a CMOS sensor and applied to bioimaging. So here is, I think 2000. This chip was developed early 2000 already for military purpose. And what happened is, here is a pixel array, like 1,000 by 1,000, and actually 640. And both sides are analog to digital converter. What happened is, CMOS sensor can read out one line at one time. At the end, if you have 600 pixels, there is 640 analog to digital converter running at relatively small speed. And using this chip, what's going on here? This disappeared. Anyway, I worked with a company who is specialized to make the fastest camera. And this was our kind of the fastest image of super resolution in a way. This is gold nanoparticles attached to transferring receptor, which is actually placed to absorb oxygen. And if it's a cancer cell, this was collaboration with a cancer researcher on campus to prove that TFR, transferring receptor, is moving much faster on the surface of the cancer cell. And indeed, we attached the gold nanoparticle and look at the motions and with high-speed camera, 10,000 frames per second. At the accuracy of nanometer, this is the center of the this golden particle. We can measure nanometer resolution. So this is the fastest nano resolution of 10,000 frames per second image. I regret I didn't publish this actually. I didn't know significance of this kind of image at the time. So you get an idea. And then, so I became a part of California Nanosystem trying to speed up any microscope to put the high-speed camera. So over the last 10 years or so, I expanded my collaborations to many different research institutes. And by the time when we published the new proposal 6 months ago, I had 170 names behind our proposal. And Brett is actually making a hand, of course, just concept. Okay, now let's step back. What we are doing is a very simple kind of a transformation. You have objects like your brain, three-dimensional object, but changing in shape and dynamic signal in time. It's a four-dimensional information. The question is how to take this four-dimensional information. To the end, it has to be read out by computer. So you have a wire from your camera to the computer. And this is typically running like a gigahertz. So the question is how to scan four-dimensional object and make it one-dimensional information. I came up with a general principle of composition of extra dimensions in a way that biological information is four-dimensional, including a fluorescence decay, it's a five-dimensional information. Or including frame rate, time delay, wavelength, including wavelengths and time delay, it's a 6 dimensions. So the name of the game is to convert 6-dimensional information to 1 dimension. And so I have a general principle, that's why I can design a different type of microscope for 4-dimensional scanning based on some principle of how to convert extra dimension. Of course, you basically use 2D Galvo, Miller, piezo, this scanner. There are many techniques to scan the volume and change it, reduce the dimension. That's what we are doing. Okay, downstairs, we have a 4-dimensional, 5-dimensional microscope. To the end, we scan the beam and convert it to 1-dimensional information. Sequentially, we put it in the computer. Application, maybe I stop after maybe 10 more minutes just to say a few words about, of course, the brain. You know this. So this is our end board. So this, we have Tensor 11, and I changed the description this morning. We don't have no scale. Scale disappeared. I have an XY scale, but it disappeared. Why it disappeared? Okay, so let's just go to everything included. Sorry, this corner, this is the time, and this is a scale. So I'm going to put a number here because it's appeared. This corner is the fastest action, like action in this direction is like a millisecond order in action potential. And the size of synaptic connection is like 100 nanometer. So in the scale-wise, synapse is 100 nanometer. In time-wise, we want to measure millisecond. That is as much as we want to observe. So if we can observe any brain, including human, at the accuracy of 100 nanometer in space and millisecond in time, that's the name of the game. The problem is, if you look at the human brain survives in time for 100 years. So this is 100 years in the logarithmic scale. The size is like 10 centimeters. If you take a 10 centimeter and 1 year divided by 100 nanometer cubed and 1 millimeter, you end up 10 to the 30. That is the number of voxels. It's the number of 4-dimensional pixels required to understand your entire life of activity. It's 10 to the 40, 10 to the 30. That makes you. I repeat, you have a life of 100 years, and it is basically your brain activity, which is like a 10 centimeter cube. If you take a 10 centimeter cube times 100 years this corner, divided by millisecond, that is the fastest time in your brain, and 100 nanometer is the minimum scale in your brain, then any one person can be expressed in information of four-dimensional space which has 10 to the 30 four-dimensional pixels. And that comes to the point it is impossible to study, of course. This is a crazy number. Now, if you go to the mass, it's 10 to the 26, zebrafish 10 to the 21, Schilling is still 10 to the 16. So if you really want to understand every activity going on in Schilling's brain, even though they have only 302 neurons, 7,000 connections, in the four-dimensional space, it's 10 to the 16. Okay? That is the reason why I think it is impossible to study human or mouse or even zebrafish unless we understand Schilling in the four-dimensional space-time. There's no way to go more complex animal. It's not just this number of 7,000 connections, because this 7,000 is changing in time too. Alright? That's what I want to say. Now, let me just say a few words about standard technique before we introduce a new technique like CT illuminations. Let's take optical microscope. Optical microscope, sorry, I don't have a scale here. Optical microscope can scan like, say, 100 millisecond to a minute order somewhere here. And it can only penetrate up to millimeter. So this is the millimeters. And for human brain, primary way of observing four-dimensional structure is positron emission tomography or functional MRI, which is like a millimeter resolution up to 10 centimeters. It's here. Now, the other technique in the time domain, if you want to look at high-speed activity in the brain, you put electric needle, you measure so-called electrophysiology, but has no spatial information. So this is a conventional technique as of today. If it's optical imaging, it's here. Functional MRI is here. Electrophysiology here. Now, by looking at it, you can conclude, if you want to understand the Schilling from the beginning to the end, there are two missing parts, here and here. And here is basically sensory motor network from the synaptic level to the entire brain. You can't study by a standard microscope. And second, if you want to look at how brain network is developed from lineage, from the cell synaptogenesis, you have to observe for a day, which is missing. So if we can develop a new microscope to cover this region and this region, in principle, you can observe four-dimensional life of Schilling. And that comes to a development of new microscope. So it starts from 4 different directions to improve. In order to get a better resolution, of course, it's a super resolutions, and you have to also go deeper. Typical microscope cannot go beyond 100 nanometer. So that's one area. You want to go faster. You want to go more gentle microscope. For each area, there's a different technique. Super resolution I mentioned already. Go deeper, it's called two-fold excitations. Go faster, it's called faster CMOS camera. And more gentle way to take a data a long period, it's called CT illuminations. So what we try to do here downstairs is to try to combine all technique and expand the limitation of today's light microscope in all directions. And especially it's important to go this way and this way because this region and this region is not covered. That comes to CT illumination questions. Now, let me just go here. I think I'm going to skip quickly, I mentioned many times. Basically, what we try to do, why we have to look at the network level is because we have a sensory signal, stimulation from the sensory neurons, and we process it by central brain activity, make a decision. And I think I convinced you that unless we see stimulation and motion and brain activity as a whole, you never understand the brain. And this comes to the point that you have to see 302 neurons altogether. And I show these pictures, I show you again. Basically, as a function of time, Schilling as a three-dimensional structure is changing in pattern, in motion. Signal comes in and make a decisions. But this signal and motion must be combined together in an internal space. And to the end, this comes to basically a change of neural activity of 302 neurons from time to the next time. So now it comes to this matrix element. Okay? So basically, what we try to do is to observe activity of 302 neurons at one time to the next time by basically having this connection already given. Typical time from here to here is about 100 milliseconds. So we want to see the entire brain activity at least 10 frames, 10 volume per second. That is a typical time from here to here. That is not so far from our current system. Now I show some example before I started to work downstairs, and maybe I stop today. Next activity I started maybe 5 years ago was some sensory signal for hearing. So if the sound comes to your ear, you have sound sensor called cochlea, which is going to basically vibrate your hair cell, and it opens ion channels. And here is a tip of the hair cell which goes left and right by moving. So this tip ring is going to open calcium ion flow. So here is an airflow. We attach that high-speed fastest CMOS camera. And this is an example of high-speed motions. Again, here is hair cell sensing the sound of the frog. We have to dissect it, so we sacrifice and cut off and look at the motions. And again, this one is 1,000 frames per second. And we are observing a motion of hair cell every 1 millisecond at accuracy of nanometer. Again. So this was the first publication using the high-speed CMOS camera of high-moving objects. So when we say high speed, typically we're talking about sampling rate of about 1,000 per second. And we can get a nanometer resolution if we are smart enough. I also show two-photon excitation, and then maybe I stop to this lecture. Before I started to move on to CT illumination, I spent most of the time on two-photon excitation. And here is the difference. Conventional microscope, as I already mentioned, starts from blue light, shoots the point, and then scattering light, not scattering, emitted light of 500 nanometer goes back to pinhole. That's what we call conventional confocal. Whereas two-photon excitation starts from longer wavelengths, like 80 nanometer. If you superimpose two photons of 80 nanometer at small localized point, and then two photons of 80 nanometer behave like a single photon of 440 nanometer. But this is a non-linear effect, meaning the square of the wavelengths only excite only the point. So here is the light path of the blue light. Here is a superposition of two of the red light. It's already point. In other words, since it's starting from the point, you don't have to focus back to the pinhole. You can collect any light coming out. It's already point confocal by having two photons at the same locations. So that's already advantageous, so you don't have to have a point. Also, tissue is transparent for 80 nanometer here, because the blood has absorption like here, but here the cell is more transparent. So idea is to shoot near infrared, that tissue is transparent right to the point, and get the scattering light. It's called two-photon excitation microscope. So now it comes to high-speed camera or detections, which I developed with Hamamatsu 10 years ago. Now it's a commercial product like a microscope. So we start from the laser extremely fast and has a very narrow pulse, like 120 seconds, and shoot. Basically, it's too complicated to explain. Basically, we separated to 4 different beams, 3 nanoseconds separated. 3 nanoseconds, each photon only travels like 1 meter. So photon is spaced by 1 meter while it comes, and we scan at different locations. Now here is a microscope at the medical schools. This is the first image of scanning. Barrel cortex is a part of the brain which receives a signal from whisker. And as you know, mouse has a very good sensitivity by moving their whisker, and there's a one-to-one match. And here it's hard to see, so what we did is basically we processed identifying 58 neurons, and this is a 240 frame per second, wait, it says. This is 240 frames per second. This is the world's fastest two-photon excitation microscope at that point 5 years ago. And from that, strange image disappeared. Sorry. By this image, we look at the correlation between 58 neurons. And then this was the end of my research in the mouse. I made the world's fastest two-photon excitation microscope to satisfy my collaborator. He said this is going to change to do a neuroscience, but nothing happened. And the reason is, of course, the mouse has 100 million neurons. We have 100 million neurons. Even if you watch this flashing neurons, it's only 58 neurons. And now I just realized why we're not making any progress. Of course, we are making such a tiny part of the brain. And you can't tell the activity. Of course, the brain is stimulated by signal coming in and also receives its own motions. Unless we see all the neurons, we can't make any advance in neuroscience. So that was 2012, I think I published the first data method paper. And that's it. So after that, I thought more and more and decided to do basically zebrafish business. It's already 1 hour, so I'm going to, let me check. I think I'm going to give a lecture tomorrow or Thursday when there is enough time. So far I introduced, so where am I? Let's get this. So basically I finished introduction, principle of microscope, superlative high speed, and two-photon excitation. So I finished this much. So if tomorrow is not too crowded, I am going to talk about sheet eliminations. That is what we have downstairs. Questions? You get the basic idea? Now it follows a principle of physics again, step by step. There's nothing secret, but you have to understand every single principle to design a microscope which is better than anyone else. And if you so here is the important principle, right? This laboratory, in principle, I promise we can design any microscope which even doesn't exist if you can do it by physics principle. Typically, it takes about 5 years for new technology like we are developing to become a commercial product. And it becomes a commercial product if there are many users. So what we are trying to do is to introduce a new concept and set up first testing here, and then move to Nanocenter. Indeed, already set up 2 microscopes over there, sheet illumination. Invite some end user, and if you have enough end user, write a proposal. And at the same time, some company like a Leica or Hamamatsu come and help. And if it's a good idea, we typically, in a good way, we file some intellectual property on campus and start some kind of starting point of the small company, or sell this idea to a microscope company, and 5 years later, that become a commercial product. Any microscope starts like this. Basically, it starts from some physicist or someone thinking deep for users' point of view and also physics principle, and go faster speed or best resolutions, and then it takes 5 years. Questions? Okay, so I've finished here, and tomorrow we have presentation of Rebecca's group with who's giving a talk. Raise your hand. I think we have some presentations disappeared. High school students.
Yeah.
Where did they go?
I don't know.
Okay, they are sitting here. What are they?
They were here earlier.
Yeah,
but they'll
right.
be here.
They maybe disappeared. So we have a presentation of thumb taxis and new development of data analysis, not based on ImageJ, but based on MATLAB directly to track the neurons, which is faster and more reliable. Not neurons, sorry. And electric field group has you want to summarize? This is something that I will continue on my microscope presentations. And then Wednesday, we have many speakers actually. I try to have a big presentation of simulation of the brain. questions? Okay, I finished. Let's go back to work.
Steve, do you want to present with us? Do you want to say some words? Okay.